Hello to everyone. My name is Gregor Pipan. I'll be moderating today's expert session. Thank you all for joining us. Let me present myself. I represent CGS Labs, an international company which is specializing in the development of software solutions for infrastructure design. Our head office is based in Slovenia. This is actually a small country in Central Europe. It's situated between Italy, Austria, Hungary, and Croatia. And why am I saying this? Why are we here today, actually? In year 23, Slovenia was hit by some of the most devastating floods in the history. And it was an event whose consequences our country still feels today. It was really a harsh reminder of how vulnerable even well-prepared communities can be. And it's not just our Slovenian local challenge. You know that across Europe and around the world, extreme weather events are becoming more and more frequent, more intense, even more disruptive. And this experience motivated us to check how we can contribute actually in this field of flood protection. And we believe that the best way to move forward is by connecting expertise across multiple disciplines. And this is why today's session brings together specialists in measurement technology, hydraulical modeling, meteorology, infrastructure design, and we want to share tools, knowledge, some real-world examples that can help all of us better prepare for future flood risks. So I would like to welcome my colleague panelists, Tomasz Pucik from European Severe Storms Laboratory in Vienna, then Katja Weber. She's application development manager at OTT Hydromet, a company that designs measurement equipment. Martin Nagel, I hope I spelled correctly, Martin. He's a hydrologist and advisor at DHI. This is an institute that develops solutions for hydraulic simulations and applications. And then also my colleague, Jan Cunja, he's product manager for hydrology solutions at our company, CGS Labs. Maybe just one more information about this expert session. I would like to emphasize that the event is being recorded as promised, and we will share the recording later on. Also, what I would like to invite you to is to post questions. You have in the GoToWebinar user interface, I think you have special sections for Q&A. You can enter your questions there. But we have 4 panelists, so I would ask you if you can write for whom the question is, so we can address those questions at the end of the last session. We won't answer questions during the presentations, just to keep the flow of the presentations in order. So now I would like to invite our first panelist, Tomasz Pucik, to share with us his presentation. Just a second. Here you go, Tomasz. I hope you received my invite.
Yeah, I did. So I hope you can.
Okay, we can see your screen. Yes, it's okay.
Can you see my presentation?
Yes, we can.
Okay, very good. So good morning, everyone. I will talk about the meteorological analysis and then a little bit of the challenges that meteorologists are facing when they are predicting flash floods. In the end, I would like to concentrate on basically the deadliest weather disaster of the last year, which was the Valencia flash flooding in 29 October. with more than 230 fatalities and enormous damage that has been caused. And of course, from the convective storms, the flooding is very local. And here what you can see is an animation of the lightning strikes over the course of the flash flood event. And these yellow crosses that you can see are the lightnings in a 5-minute period. And you can see how they are accumulating basically over one spot. So we had the storm residing over the Valencia area for several hours straight, and then a very intense storm. And then by the end of the presentation, you can see that this storm begins to just very, very slowly creep out of the area, but it was hovering there for many hours. So what about the rainfall intensity and its duration during this event? So based on the graph that I'm showing below from a Turin station from the IMET network, the highest 10-minute rainfall accumulation was 42 millimeters. So from the meteorological perspective, this is a tremendous rainfall intensity. I can say that I have barely seen something like that happening in Europe. So this is really a huge amount of rainfall. So the storm that formed really produced extreme rainfall intensities. But it was also during a prolonged amount of time, because some of the storms, it rains very heavy, but not for a very long time. In this case, for example, in 30 minutes, there was more than 100 millimeters of rainfall, or 100 liters of water per meter squared. That's like an equivalent unit. In 1 hour, more than 180 millimeters of rainfall. Again, quite a tremendous value. But what you can also see from the graph is that it rained with such a very high 10-minute intensity, exceeding 20 millimeters per 10 minutes for several hours straight. So in the end, we ended up with a total 24-hour accumulation of 771.8 millimeters. Now, what is tremendous about this, of course, is that if you imagine that there are many places in Europe where the annual rainfall is less than this, a majority of these 700 millimeters fell in a 6-hourly period. So imagine your annual rainfall falling in 6 hours of time. So that is something really, really incredible. Now, when we are talking about the convective heavy rainfall events, when we compare it to the rainfall events that are tied to deep low pressure systems or some fronts, cold front or so on, they are very, very local in scale. And when we look at the precipitation sum and its distribution across the whole Valencia area, you can see that we have a narrow maximum. And then when you go from this maximum of 300 to 800 millimeters, if you move like 10 kilometers to the east, you will get in the zone where it basically didn't rain. So that is an enormous challenge and something that we still haven't tackled in the meteorology to forecast the precise location of the rainfall from the heavy convective storms. This is something where we are still not there. Now here I'm animating a weather radar from the location, and you will see the development of this band of heavy rainfall over the area. And then you can see that first of all, it resides basically over one location, but also look how narrow the zone of the rainfall really is. So of course, if the rainfall moved 20 kilometers to the west or to the east, the situation and the impacts would be very different. They would move from one area to another. How do meteorologists approach forecasting heavy convective rainfall? Well, we try to split it into two different components. The first is forecasting intensity and then the duration. So for the intensity, we are asking ourselves how much rain is going to form in the cloud. And for the duration, we are asking ourselves, will there be conditions that will enable the storm to remain over one location, so that a huge amount of precipitation can fall for a prolonged amount of time, so that eventually we are getting into these rainfall sums exceeding hundreds of millimeters. Now, what about the intensity? So here we are looking at the photograph of what we call a cumulonimbus cloud or a storm cloud. And what these clouds are comprised of are very powerful updrafts. So there are actually measurements of the updraft speeds that are reaching 50 to 70 meter per second. So imagine the air in these storm clouds can rush faster than how you can drive on your highway. Well, except if you're in Germany, right? Then you can drive very fast. But the air really rushes up very fast upward in these storm clouds. So we flux a lot of water vapor up, and we can have really tremendously intense rainfall formation processes in this cloud. What will the intensity depend on? Well, the first of all is there is some air flowing into the storm, how much water vapor availability there is in the inflow to the storm. So what is basically the water content in the air near the ground? Then how powerful these updrafts in the storm clouds get. So how much vertical flux in the water vapor it is, and this scales both with the updraft speed but also the size of the storm overall. And the third factor is if the rain forms in the cloud and it starts falling to the ground, how much of it is going to evaporate. And let's investigate some of these things. So now we're looking at the weather charts from the event from the 29th of October 2024, and maybe not all of you are familiar with this type of chart, so I will guide you through this. What you see in here are some colors, and then we are going from yellow to blue, and the blue corresponds to a lot of moisture. So there was moist air coming from the Mediterranean Sea towards the Valencia region, and you can see that the arrows in here, either shown in the gray, or I highlighted them also in the white, they are very long. So there was a strong flow of moist air coming from the sea towards the Valencia area, and this was happening for actually a larger part of the day. So we had a strong moisture advection. And this moisture, it is one of the ingredients for these heavy rainfall events, but also for the development of the storm clouds. And then we see this red contour, which I highlight in here, and this corresponds to an area with a very strong temperature decrease with height. And this cumulonimbus, these storm clouds, they like when there is a strong temperature decrease with height, because the air in the storm that rushes upward has to be warmer than the surrounding air, and it can get much warmer than the surrounding air if the surrounding air cools with height very strongly. Now, what we get of the combination of these two, of the moisture and strong temperature decrease with height, is that there is high amount of potential energy reachable for the storm. So in the meteorology, we have an index that is called CAPE, convective available potential energy, and there was really a lot of it for a long time over the Valencia region. Then you see some of these, so this is this orangish reddish area that you can see in here, and then we have this area that is sort of whitened out, and this is the potential energy that is not actually reachable for the storm. So there is like a stable layer or a lid that would prevent the storms from using that. So exactly over this Valencia region is where we had the best presence of available energy for the storms. And not just that, what we also got over an area was there was both this high potential energy for the storms, but also what we see is an index in these bluish reddish colors that shows that there is a lot of change in the wind with height. This is a condition that we call a vertical wind shear, and it profits storms, heavy convective storms, a lot. And then why is that? This vertical wind shear creates a horizontal tube of rotation, of vortex line, that is ingested by the updraft of the storm, tilted in the vertical and stretched, creating sort of an ice skater effect. And this rotation in the storm is basically like a huge vacuum cleaner. It sucks up the air from below. So in the end, what we get is that the updrafts of these convective storms, when we have rotation in the storms, are much wider and more intense compared to the storms that do not rotate. Yeah, once again, it's like a big vacuum cleaner when the storms begin to rotate. So also there was very strong vertical wind shear in the environment, and the storms that were developing were really sucking up a lot of this moist rainfall upward. So we had a tremendous vertical flux of the moisture. Now, what about the duration? Now, that is a big thing. Yeah, we had a very intense storms. And now, what about the duration? So I'm now animating the satellite imagery where this colder colors represent very cold, very powerful storm tops. And then you can see that these reddish, the reddest colors, stay precisely over the same location. I will animate once again so that we can get an overview. So once again, track this, the reddest color in here, right? So we see that the storm, the strongest updrafts in the storm were sitting exactly in the same spot for several hours. And this is what in the end made the situation so tremendously dangerous. How do we get this high duration of the rainfall? There are a number of ways. One of them is whether we have these favorable ingredients for the convective storms or for this heavy convective rainfall remaining over one area for prolonged amount of time. And this is precisely what happened. We have this flow of very moist air coming from the Mediterranean Sea over the area, basically for the majority of the day. And now let's notice the physical geography of the region, right? So we have this moist air flowing towards the Valencia region, and of course we have a local terrain. And what is especially important for us are these small mountain chains over here, because these actually started triggering the first storms, and then the storms that formed tracked over the Valencia region. So what happens? We have a moist air coming towards the mountains, and the mountain is a barrier. So the air that approaches it, it has to go up. And as the air goes up, this actually triggers the development of the storm. So as the air is forced to rise up, this also starts this release of this potential convective energy, and we get a storm. Yeah, and it can rain over the mountains. And as long as we have this moist air flowing towards the mountain, the storm can basically hover over it for a lot of time. Or what we can get, of course, the storm, because it rains and some of the rain evaporates, the air gets heavier underneath in this precipitation area, and it collapses down. This is what we call a downdraft in the meteorology. And some of this downdraft air, it can rush down the mountain slopes and out from the mountains. Now remember, we still have this very powerful flow of air rushing from the sea towards the mountains, and you can imagine what happens when this outflow from the storm hits the inflow from the sea. Of course, because of the mass continuity, we cannot go with the air underground, so we have to create an updraft. And on the zone of this low-level convergence, we have a cloud formation, and this serves as another trigger for the storm. And if the wind direction stays the same and the situation doesn't change, and this trigger for the storm stays at one location, we will have this situation when we have the formation of the new storms over this spot, and then the maturing storms with very heavy rainfall will continuously move from this spot over there. So if we have this moist flow of air, and if we have these convergence zones residing over an area for a couple of hours, then we are getting heavy convective rainfall for a couple of hours. And this is, by the way, precisely what happened in this situation. So we had this air filled with high energy, 2000 joules per kilogram of this convective available potential energy, or what we call K, rushing towards the sea, towards the Valencia region, and then the orography triggering the convective development at this spot for several hours, and then the storms being carried by the mid-tropospheric wind further inland and deeper into the mountains. But if the situation with the favorable inflow of air persists for many hours, then it will rain for many hours. Now this is a little bit more of a description of what kind of, let's say, ingredients for heavy convective rainfall that the meteorologists would be looking at. So for example, concerning the intensity, as we said, we are looking at the high water vapor content in the atmosphere. We look for the sufficient energy to sustain strong updrafts. Then we look whether we have the strong vertical wind shear present, the low cloud bases. So I can explain this for low cloud bases. This is important because if we have very low cloud base, then the rain that falls out of the cloud base and will head towards the ground will have little time to evaporate. Yeah, if we have very high cloud bases, like in some very continental clouds, then a lot of rain is going to evaporate on its way to the ground. And then a high level of 0-degree isotherm. That is quite interesting, but it is actually sometimes quite important, because the higher the level of 0-degree isotherm is, the bigger portion of the cloud where we will actually have a formation of raindrops. If the 0-degree isotherm is very low, then the storm will be in this very cold part of the troposphere, and instead of the raindrops, we will be more forming ice crystals, let's say, in the upper part of the storm. So for the duration, what we're looking at is either there is a very weak wind in the whole atmosphere, so the storms will not be carried by the wind anywhere, or if we can identify that we are going to have this very stationary triggering mechanism that will send the storm cells over the same location for several consecutive hours. And you can imagine that this is actually pretty difficult to forecast, this stationary storm trigger mechanism. This is, by the way, also what the numerical models struggle with. Here, what I highlighted in orange are the ingredients that are impacted by climate change, or that the current existing literature suggests that it is being impacted by the climate change, which is the water vapor content in the atmosphere and the energy available for developing storms. This is owing to the warming of the atmosphere and more potential for water vapor or evaporation over the Mediterranean Sea. Then the 0-degree isotherm obviously is also increasing, and there is also some literature that suggests that overall, for many of the storms, the mean tropospheric wind will decrease, so we'll have a higher fraction of the slower moving storms in the future. So, as already was mentioned by Pipan, the climate change can negatively affect these events in the way that they may become more frequent in the future. Now, a little bit philosophically speaking about the what are our capabilities of very heavy convective rainfall. And I was personally looking several days ahead of this event, or one day ahead of this event, and it was very clear that there is very favorable environment or favorable overlap of these ingredients for the heavy convective rainfall over the Valencia region. So it was quite clear that the situation is going to be serious, and that is what the meteorologists are capable of saying. Now, with the heavy convective rainfall, where the big problem comes is that the exact location, timing, and the highest rainfall amounts are uncertain. And then in the end, this timing, yeah, because it often rains very intensely for a short amount of time, but it is hard to predict whether that will be at 12 or let's say 15 UTC. And also the highest rainfall amounts. So the models struggle with forecasting exactly how much rainfall is going to fall with this with these convective events. And in the end, I haven't seen a single model scenario that would predict in this Valencia case that we would have over 700 millimeters of rain. Part of this problem in the location, timing, and intensity uncertainty is solved by using so-called ensembles of the model. So we run a lot of numerical models, or for example, 50 or 20 different runs, and each of the run is very slightly perturbed to the other one. So we create like a host of simulation to sort of compensate for this butterfly kind of effect, because we are never sure what exactly is the initial state of the atmosphere. But even with these high resolution ensembles of the numerical forecasts, we still have very hard time nailing down exactly how much rainfall is going to fall and what will be the exact location and timing. What we are very good at nowadays is saying that this is a situation that may really produce very heavy rainfall. Okay, so thank you for your attention.
Thank you, Thomas. This was quite insightful. Now, I would like to invite Katja Weber from OTT. She will be sharing with us some information about how we can measure weather events, how we can predict where the potential floods are going to happen, following, for example, how the river flow, river level rises, maybe how we can set alarms on certain infrastructure objects so we can act accordingly. So please, Katja.
Yes, thank you. I think you should already be able to see my screen. I hope it already shared.
Yeah, yes, it's visible.
Great. So I won't waste much time on introducing myself because Gregor already did that. Thank you. But yeah, as you just heard, we focus on the measurement technology for environmental parameters. And in my role as application development manager, it's basically my task to help to find the right solution for what our customers need to do. They face a specific problem they want to solve, and I help to find the right technology, the right measurement principle to solve their issue as good as possible. And with that, I also developed a strong focus on the flood management, specifically in cities and communities. And that is what brought me here, why I was allowed to attend. And I would like to start out with what do we mean, to give you an overview what we mean when we talk about measurement technology. Because the first thing everybody thinks about is the sensor, of course. But measurement technology means way more than just a sensor. It is always a concept that you have to plan, and that is what makes it so challenging for some people, specifically if you do not have the experience with all the different options that are available. But it's also what carries a lot of potential in order to actually help us. So we do have the sensors, of course. You see them on the left side of the screen. Could be different sensors based on which parameter you are interested in. Could be actually related to water, like water levels or precipitation, but we could also measure wind speeds, wind direction, humidity in the air, all things that could trigger potential events. And now this one is really focused on flood risk management, since this is our topic for today. And then the most important point is not just to measure, but also access your data and be able to interpret your data. How do you visualize them? Maybe also for people that have to make decisions, but that are not necessarily familiarized with the station itself, with the sensors itself, of all the setup, and that might create challenges interpreting the data. So how do we visualize that? How do we create access? That also includes data remote transmission. How do we get the data from our station to your office, to your smartphone, to your tablet? There are a lot of different solutions. And this is why we say, please, it's all about planning a full concept. And there's not that one perfect flood risk management station, but it will always be about look at different pros and cons of different options and then combine those options in a way that they make most sense for the challenge that you have to face and that you have to solve. And that is what we're also there to help you with. So always keep in mind, it's more than just a sensor. Measurement technology means a whole concept, a whole system. It also even planning a complete network of things to make sure you have access to your data when it matters. And the second thing I would, before actually going to the technical solutions, would be, why actually should I measure? This is and I have that in here because this is a discussion that I quite often face when talking to customers. And the two main things that we hear is, if I measure it, it's too late anyways, I need a forecast. Or why should I measure myself? I could just use the data of my local weather service. Both absolutely valid points. For the forecast topic, we just heard Tomasz mention how challenging it can be to forecast specifically these local heavy rain events. But if you are in that moment the person that needs to make a decision in order to act, in order to protect lives and values of people, do you want to rely on a best estimate on a most likely scenario, or do you want to actually know what is going on? And now, I don't want to say that forecasts are bad. In contrary, we need them. They are a very important part of us being able to respond to an event, because they provide us information on what do we need to prepare for, most likely. But they also have the challenge of just being a best estimate. And in the moment where you have to respond and where you have to act, you might want to have actual data, sound information on what is going on specifically at this river, specifically at this station. And this is why we would want to measure. Another thing is also that maybe afterwards you would like to have sound information on what happens, because unfortunately, quite right after the event, often it's about responsibilities. That is the first discussion that people start, even though there are many other things that we should focus on, but who is to blame? And then if you would be the one to be blamed for making a decision one way or the other, then you would like to have data to defend your decision. And again, these data should be accurate and they should be reliable. And you don't want to stand there and say, oh, but it's at most likely it's going to turn out like that. For sure, this is an information that you use up front to start planning. But still, in the moment when it matters, you need sound information to make your decision. And we have one example here that is already from 2014, but we still like using it because back then we were lucky enough that one of our sensors was actually in the center of an event. And the maps that you see here are the data that the German Weather Service would provide. And on the left side, you see the online data, which are the ones that you could get with the least time delay. Basically, these are the data you can get pretty much instantly. And you see back there, they forecasted about 150 millimeters in 12 hours. So you see our station was at where the arrow is pointing, and that is really in the center. And there they forecasted about 150 millimeters in 12 hours. And then later on, they used the data of their ground-based measurement stations, so with actual measurements, to calibrate their model. And after the calibration, they came up with, they already switched from 150 millimeters in 12 hours to more than 200 millimeters in 12 hours. And this is also pretty much the upper end of their scale. You can't get more accurate information. It basically just said, be prepared. Something is going to happen. And also something did happen. And here we have the actual data that our station measured. On the left side, you can see a photograph of the station. This is a precipitation sensor with the weighing principle. I like to highlight the detail with the clothes in the background because there was a heavy rain event. People had to be out. So what actually happened in the end was almost 300 millimeters in 8 hours. That's quite a difference to what we could what was forecasted. And that difference could mean that your emergency service would be completely surprised by what is going on. I also have this nice example for, we might have people in the call that are not so familiar with precipitation amounts. Almost 300 millimeter means almost 300 liter per square meter. And this is what they put together here in buckets on 1 square meter to give you a visual impression of how much water that was in 8 hours. And if you think of that you were about 100 millimeter off because you expected more than 200 and in the end it got 300, that would be almost a complete layer less. Okay. And that amount of water would not stay on that square meter. That is the difficult thing about the flood risk management. The water doesn't stay on the square meter where it's falling as precipitation, but it will move downhill, and at some lowest point, it may accumulate. And this is where you suddenly get a problem because you get a few of those layers more than you expected. So as I just said, that could surprise your emergency services, which would then waste potential time and resources in responses that are not actually fit to the amount of water. Imagine they, out of experience, they would know that with this amount of water, with 200 millimeter, we usually get problems down there, but never up here. So they would never check further up. They would always go down to the place where they expect something to happen. But maybe if they would have known that it's actually way more water, they already would have checked somewhere else where they could have made a difference as well. So with not being fully informed, they might waste time and resources to help where they are needed most. And another thing you could think about is your local wastewater treatment plants. Quite often they are allowed to spill untreated wastewater in order to prevent bigger harm. If there's so much wastewater or also rainwater that they can't fully cover that amount. But they are only allowed to do that in very, very exceptional situations where there's really no other way to protect from a bigger hazard. And they have to prove that afterwards. If they can't prove that the situation really required that, they will have to pay high fines. And that is important because otherwise they could always just spill untreated wastewater and say, yeah, but it was exceptional. So they have to prove that the situation was exceptional. And 100 millimeter difference could make all the difference for them to prove, yes, it was exceptional or not. Or think about insurance claims. If an insurance has to pay or not, afterwards they might say, yeah, but we don't have to pay because the event was not that exceptional. And if you can prove that at this specific location, it was 100 millimeter more than what they said in the forecast or what the German Weather Service predicted, then they will have to pay. But without the data that you measured, you might not be able to prove that. So there are a lot of reasons why it's good to have or important to have sound information. And with this picture, I just want to come back to pros and cons. Again, the data of the German Weather Service are a very important part to use in your response. They give you a first information on what to expect and early information on what to expect. And they give you a very good overview on the spatial distribution of the event. But they also have a challenge, which is specifically the accuracy for these local heavy rain events, as you can see in this picture here. Because they always just have one value per measurement cell, and a measurement cell is relatively big. Based on the weather service where you are, it could be like half a square kilometer or 1 square kilometer. This is the size you have to think in. And if you see this precipitation event, that does not cover a full square kilometer. So out here, you will get precipitation measurements that are overrated. And in here, your value will be highly underrated because you also have zero precipitation, which is included in your measurement. So again, the best option is to use a combination of things to get the advantages of all the different systems and cover up for the disadvantages that they might have. It's a bit unfortunate that there's not one perfect solution, but that's why we're here today to talk about it. But let's start with some examples of what can you measure, how can we measure it? And I will start with the precipitation, because precipitation is the first parameter we can actually measure. So we can upfront, we can have the information from the models with a bigger overview, but thinking about a flood scenario, the first thing we can measure is the precipitation, and that would lead us to the longest pre-warning time, and that works specifically well if the precipitation runoff connection is well known. So I once had a customer that told me, yeah, every time it rains up there in the vineyards, about 15 to 30 minutes later, our main street down here is flooded. So in that case, it would indeed create 15 to 30 minutes pre-warning time for them to actually respond, to potentially block the road, and things like that. Or to also hold the water back. They would have a chance to control the water if they were aware of what's happening. So in these two pictures, you see an example of a precipitation measurement with our Pluvio a pluvio is a precipitation sensor according to the weighing principle, which means actually a big bucket on a scale. And we measure the weight of this bucket, and every raindrop that falls in there increases the weight. And with that, we can very accurately measure precipitation. Weighing principles are specifically suited for heavy rain events, for exceptionally high rain events, because they have no limiting factor towards the amount of water. Right, so they have no small funnel that could be blocked or that could delay the amount of water or something. They are really suitable for heavy rain events. They have the slight disadvantage that they are very bulky and very big, as you can see on these pictures. So in urban areas, it could be very difficult to install them, to find a good installation place. It's not much of a problem if you have your own ground somewhere, maybe they are even fenced and you can put it on your own wastewater plant or locations like that. And on the right side, you see a solution for an urban area. They place the precipitation sensor on top of a flat roof, which is a really nice solution. On top of flat roofs is in urban areas quite often a very good option. Just please be aware you need to get to this sensor about once to twice a year, at least. So it should be accessible. On big flat roofs, usually that's not that much of a problem, but be aware it should be accessible. You can see in those pictures that the systems are solar powered. We have the solar panels here on the right side on the right picture, and on the left picture, we have it right underneath the sensor. So these sensors can be completely solar powered, even though for precipitation measurement, if you have mains power, it's always advised to use mains power if it's somehow arrangeable without too much of a hassle. But yeah, as I just said, this weighing principle is not always the best choice because it is very bulky and sometimes difficult to find an installation place. So we do have other options. On the left side, you see our WS100 sensor, which is working according to the radar principle. And this one is specifically small. You see it's very, very compact, and it has zero maintenance, so it will always work. It's very reliable. It's great to install in urban areas. You can install it pretty much everywhere. It's also less expensive, so you could, instead of having one station at one spot of your city, you could probably buy several stations with this sensor and spread them over the city, which would allow you more information on how the event is spread over your city. Is it maybe more in the eastern part of the city, more in the western part, or is it your whole city being under heavy precipitation? So, but before that sounds too good to be true, also this one has disadvantages. And for that sensor, it's mainly the accuracy, which is under field conditions about plus minus 20%, where a weighing sensor would manage plus minus 1%. So if your focus is an accurate measurement of the amount of water coming down, rather choose for a weighing sensor. If your focus is more on, I want to know what is going on where, and I want to get a good impression on how the event is spread over my city, a radar sensor could be a better choice. On the right side, you see a third measurement principle, which is called a tipping bucket. That is very, very widespread, a commonly used device. They are inexpensive, they are simple. For the heavy precipitation measurement, they have the disadvantage that they have a funnel that could block, and that regularly needs to be cleaned. So you really need to go to that sensor every few weeks to clean it. And it has a high risk of not working the moment it matters most. So imagine, what does it mean to you if you were responsible for getting a warning system for potential flooding situation, and you decided for this sensor, and then in the moment of a heavy rain event, unfortunately, this sensor is blocked because there's some leaves in there or some dead insects, and you don't measure the precipitation in time or not the full intensity because it's just the water is held back in the funnel. So as you can see here, if this funnel is blocked, the water is held back, and then you won't measure it in time. You will measure it with a delay or not at all. And what does it mean if that was your decision to make? So I feel it can be a very suitable solution, specifically if it is installed right in front of your door and you can have a look every day, then go for it. If it is a bit further away, you have to think about the fact that it needs a very, very high level of maintenance, and it might be the least reliable solution for measuring heavy precipitations. So just a very little detour. I won't make it too long because I'm already a bit too far in time. Soil moisture measurements. They can be very helpful input because a precipitation, the same precipitation event can lead to a completely different outcome based on the actual soil moisture. So, and it's very easy to add a soil moisture measurement to a precipitation measurement station. This is really, you just have to add the sensor. It can be connected to this data logger in there. It can be connected to the same power supply. So all you have to do is add one sensor and you get additional information that can be very valuable and that can help you predict what is going to happen more accurately. It's also a good input for models. If you use models to forecast events, this is also a valuable input. So consider it, be aware, it's very simple, very easy to add, and it can provide a lot of benefit. And now I will get to the second very important parameter, the one that you immediately think of with flood warning, is the water level. And for water level, we have a lot of different opportunities to measure it. And it often depends, what is the best depends again on what do you want to reach and where are we measuring. On the left side, you see a photograph of an actual flood monitoring station that was used for a city here in Germany. And they said, yeah, we regularly have issues with heavy precipitation event. This river gets too high and then the bridges get flooded and we don't want, we need to know in time. And this station could be mounted right next to this bridge, which was convenient. In the front, again, you see a little switch cabinet that contains a data logger and the battery and the solar charger. Again, you see the solar panel. The system is completely autonomous, only solar powered, because this bridge is a bit in the middle of nowhere, so we would not have mains power. And the sensor is in that case not yet mounted. It was in the end mounted right underneath the bridge. And it was a radar sensor because we had the benefit of having a bridge available, so it was easy to get the sensor above the water. And a radar sensor, like the one you can see here on the top, has the big advantage for flood monitoring systems that it is outside the water. So it has a low risk of being harmed due to debris floating in the water or just due to very high flow velocities. This sensor is outside the water, so it has a low risk of being harmed and a high chance of measuring through the full event. The only time this sensor would not measure anymore is once it's getting completely flooded. But you see, this might already seem complex to you that you have the station on the left side and then you have the sensor there, and it's a lot of things. I agree, it's still a relatively big setup, and that is why we also develop smaller, more compact systems. And we have two things that you already see on the slide. One is called the EcoLog 1000, and the other one that is the one that you see on the bottom. Well, it's written on there, so I guess you can see it. And the other one is called Flood Monitoring System, and that is on the right side. The EcoLog 1000 uses a pressure probe. That is the biggest difference between them. The EcoLog 1000 uses a pressure probe, and the flood monitoring system again uses a radar sensor. Pressure probes need to be in the water, so they have a bit of a higher risk. But in general, which one to prefer is only based on how can we install them. A radar sensor needs to get above the water, and based on your location, that can be difficult. But I will show you some examples how with these compact systems, we can really create very basic setups to measure the water level. Maybe for your information, all the heart and brain of the system that is usually in this cabinet that you see on the photograph for the EcoLog 1000, it is in this white tube that you can see. In there is a modem, and there is the battery as a power supply, so it's battery only. And in there, we also have a data logger. And for the flood monitoring system, you have it in that little case that is in the middle of the photograph. Also there you have batteries or a solar charger, because there we have a solar option available. And you would also have the modem in there and the data logger in there. So these systems are very compact, and they have the huge advantage of being compact and simple. They are ready to go. You don't have to plan anything more. They have the disadvantage of what you see is what you get. So if you want to add other sensors or anything, you can't do that. It's just this setup. But yeah, this setup is specifically made for basic water level measurements that you can install pretty much everywhere. You see this photograph, it was a small stream that wanted to be monitored also specifically for heavy rain events, because these local heavy rain events, usually we don't have to deal with the big rivers. The small rivers are really the higher, they carry the higher risk in that case, because they suddenly get so much water that they can't take it, that they will flood. And here you see the sensor itself is sitting, the sensor itself is sitting in this tube down here going into the water. You can see, you can spot it there. And the data logger part and the modem part are sitting in this vertical tube closed with a well cap that is out of a plastic, which allows the cell phone signal to get through to the modem. So this is a very basic setup also here with screw foundations. So you don't even need to drill, you don't even need to prepare concrete foundations. That is a setup that works nice also in environmental protected areas, because it's such a small influence, but providing the benefit of having data. This is a very simple setup that you can often quickly install. You can do it even more simple. If you don't want to use screw foundations, use a wooden pole. So you see, you just need to be a bit creative. All you need to manage is get the sensor into the water and make sure that the data logger part stays dry. These are the two important things. For the rest, you can have a lot of ideas how to install that and how to mind that. And now you might question, yeah, well, if it's that easy, why would I ever invest more money and more work and more effort to get a level station set up? Because sometimes it is not that easy, and sometimes you have different situations. So in this case, you see a photograph of our flood monitoring system. You have the radar sensor, which needs to be above the water. You have this case, which contains the modem, the power supply, and the data logger. And in that case, you see it's a solar powered device. So you also have a small solar panel. You can get the whole system above the water all in one together, the way you see it here, very closely mounted. And that provides you with the benefit of non-contact measurement. But that might be difficult for any situation where you have branches covering the water surface, or where you have grass growing through the water surface, anything that would reflect your radar signal. So for the ones who are not so familiar with the radar sensors, you have a radar signal go down here, and then it's reflected, and you measure basically the distance to water. So the sensor needs to be over water. The rest could also be installed somewhere else, wherever you would want. So that is really a high flexibility. This is then easy accessible for maintenance, for example, or for installation. And sometimes you might even want the camera. So I showed here a solution where we also use the camera. This is the actual camera picture of that station at night. So you can see the staff gauge there. And we would have the radar sensor. Again, we use a long arm to get it above the water. And this is a photograph of such an arm that we can use. And yeah, I'm sorry, I have to hurry through a bit now, but I will do to make sure we stay in time. And where this could be specifically interesting is rain retention basins. So here you see an actual photograph of the final station. It has 2 solar panels to power it. It has 2 cameras to provide insight of what is happening on the station. This is also connected to a precipitation sensor, which you cannot see on this photograph. It was further up here. And we again have a radar sensor. These colleagues used, so a rain retention basin usually has an outlet. And you see we have one station above on the inflow side of the outlet and one station on the outflow side of the outlet. On both sides, we would measure the water level. And in a heavy rain event, the inflow side of the outlet, we would get a high water level because the retention basin gets filled. And then they would also see what is happening on the outflow side. Do we still have outflow, or is the inflow potentially blocked? Because what you usually have is that you have these racks in front of the outflow so that they don't get blocked that easily. But even these can get blocked with debris that is coming along, and then the water can't get out of the rain retention basin. So this is an actual camera picture of one of these two cameras that you just saw in the photograph. And with that, they can check the situation at their rain retention basin, and they will know if it's necessary that they have to respond, if they have to go there to potentially clean that, if it is safe to go there to clean that, if they have to take specific material like heavy machines to be able to clean that. They will exactly know what is going on here, and this is how they will exactly know how to respond. And you could also have same system for blocked culverts that go underneath a road, right? Otherwise the road might get flooded because the culvert is blocked and the water can't go through. If you see that in time, you measure a water level distance upstream and downstream the culvert, and with that you could respond, get a camera picture, and you could see what's going on, and you could see if it is worth sending someone there to clean it or not. So that is a very specific application we use quite often, and I thought it would be nice for you to, yeah, just as an inspiration, where could it actually help? Which benefits do we gain? And last but not least, this is more for you as information to later on use it. Data transmission is a crucial part of planning the whole setup. There are a lot of different possibilities for transmitting your data. I put some of them down here. So if you ever have questions on that, we can use most of these possibilities. Well, we can use all of them that are on here, but we can show all of the different options that you have. So plan that. Please make this part of your planning to be aware. Now, the main takeaway that I want to have for you is A, measurements are important to make informed decisions. So don't push them away. They are important and you will need them. The second one is that there is not the one solution, so you will always have to plan it. But many things are possible and not even that complicated. So they might seem complicated for you, but for us, it's our daily business. So just ask us. Most likely we are able to solve it. And it might just be a blink of an eye for us because we do it on a daily basis. So I'm sorry that I went a bit over time. I hope you forgive me.
Yeah, thank you, Katja. Yeah, we'll hurry up to our next presenter. Now we have come to the part where we will see some real life projects. First, I would like to invite Martin to share with us a project designed on lakes in Switzerland. Just a second, let me share you the right. So I think you're set to go.
Yes, 1 second.
Okay, we see the presenter view at the moment.
Yes. Okay.
Okay, now we see a presentation. Okay.
Yeah, I think that should be fine.
Yeah, should be.
Okay. Good. Okay, well, when I start, thank you. So I'm going to present about the benefits of a decision support system for lake management in Switzerland. And Switzerland is often called the water castle of Europe, as it includes many lakes and rivers. These lakes have multiple roles, such as for water supply, hydroelectric power generation, tourism, transportation, or for biodiversity. And some lakes you might know are, for example, the Lake Zurich or Zürichsee, the Vierwaldstätter See close to Lucerne, or the Neuchâtel, Neuenburger See, or the Genfer See near to Geneva. Well, what some of you maybe don't know is that most of these lakes are regulated. And this means that it is predefined how much water will be released, taking into account natural fluctuations, as well as the needs of different stakeholders. And now I'm giving 2 examples. First, the Lake of Zurich. The regulation happens around 2 kilometers downstream at the river Limmat. Based on the data measured lake level, the flow through the weir is predefined in the rules of regulated discharges. This was historically set up for shipping purpose, however, nowadays it is much more complex and tries to satisfy different needs. The second example, the Lake of Biel. It is an important lake as 2 upstream lakes and about a fifth of the area of Switzerland drain through it. Depending on weir regulation, water can flow even backwards and into a much larger lake called Neuchâtel or Neuenburger See. So in total, around 2/3 of the area of Switzerland drains through regulated lakes. So let's look at how these lakes are managed in Switzerland. There are 2 levels, the cantons and the federal authority. Switzerland has a federal system of government with 26 states, and these are called cantons. The management of these lakes is the responsibility of cantons, and each of them have their own management strategy. One example being the rules of regulated discharges we just saw before. If more than one canton is impacted by the regulation, there are intercantonal agreements. On top of these cantons sits a federal authority for the environment, the BAFU. According to law, the BAFU has the overall supervision of the lake regulation, and in emergency situations, it is responsible for flood warnings and has a say in the deviation from the discharge regulations for many lakes. There were some big rainfall events also in Switzerland in the past, which led to flooding and severe damages. The biggest impacts were seen around the lakes at the northern verge of the Alps and along the downstream rivers. After analysis of flood events, it was found that the regulation of these lakes can play a crucial role because the timing and quantity of lake outflows can influence the magnitude of damage. And for example, in advance of a potential flood, lowering the lake level to gain additional storage volume can help reduce the near lake and downstream flood risk. As the crucial role of the lakes was understood, the BAFU identified a need for operational flood management. As you can see here, many lakes are connected through rivers and canals, and the forecast of magnitude and timing of flows can become complex. I'm giving one example that shows the complexity around the Lake of Zurich and the need to look at the system holistically. So here's Zurich at the bottom. You remember the downstream weir over the river Limmat, and there's a big catchment upstream which drains through this weir. But it's not only the Lake of Zurich which contributes, but also a second lake further upstream called Walensee, which is connected through a canal and which is located in different cantons in St. Gallen and Glarus. Right downstream of the weir is a junction of the Limmat with its largest tributary, the river Siel, which has a significant and almost alpine catchment. This means that the river levels can rise very quickly, conveying a lot of water into the Limmat that can lead to further flood risk in Zurich and downstream. To dampen the peak in the river Limmat, the weir can be increased, which means the Lake of Zurich is holding water back. Now, if we travel downstream along the Limmat, we meet the river Aare, and this Aare gets lots of water from other cantons, for example, from Bern and region around Bern. So any hydrograph we see here is partly an outcome from the regulation around the Lake of Zurich, but also at different regulated lakes around Bern. So you can see that we cannot just look at the at one canton or lake in isolation, but need to look at the entire country. So holistic lake outflow management becomes crucial for countrywide flood management in this case. And that's why we identified the need for operational regulation and forecasting and engaged my company, DHI, to develop such a system. So the start of the operational system is a 1D hydraulic model. It includes regulated lakes and downstream rivers. Lake regulation has been implemented as gate structures with specific control rules. This hydraulic model was then integrated into an operational system, ultimately being one of several components. Over time, a powerful decision support system was established, making continuous predictions of water levels and flows for the entire country up to 10 days in advance. There's a back-end component called Mike Workbench, which is mostly handled by us, by me and my team, and a front-end component called Mike Operations, which is mostly used by the BAFU. And of course, everything is connected through a database. So the system includes many workflows we call jobs, which run at specific time intervals. The main job currently runs several times a day and includes many different tasks related to data pre-processing, model runs based on different weather forecast data, and model result post-processing. There are many other jobs like database maintenance, backup, and log file exports, or the sending of alert emails. Everything is tailored to BAFU's needs with inbuilt tools and multiple of our own Python scripts. There's the option for the BAFU to run scenarios for every lake release, as well as giving other stakeholders access to parts of the system. The current role of my team in this project is to ensure that all workflows and simulations are operational at all times, and also on all three servers. We have a developmental system, a test system, and a production system. And in addition, we are currently expanding and improving the system. So for instance, in this year, we are planning to add more lakes and hydraulic features to the system. And we are also improving the workflows and data quality constantly. The BAFU uses the system on a daily basis. If there's no flood event, it is used to check the current lake levels and forecasted inflows and anticipate possible floodings. Before a forecasted flood event, the system is used to assess the impact of lowering the lake levels. And different scenario runs support the decision-making process for weir releases. During a flood event, flood alerts are updated based on the model forecast. And then, of course, after a flooding event, alternative scenarios are run and further analysis done since data and models are continuously backed up. And the system also can be restored at a past point in time to check certain data points. So as a summary and outlook, first, I want to say that the operational lake management system offers the BAFU tool for improved lake control and flood management. Next, the system started as a relatively simple 1D hydraulic model and over time became a fully automated decision support system, providing countrywide forecasts and managing as well as visualizing of various water data. The system enables the BAFU to support the cantons in crisis situations with advice on optimal lake releases that minimize the impact in the overall system. More stakeholders will be trained in using the system, and the collaboration with BAFU will go on for many years. We have a long-term contract, and we are constantly brainstorming together which new features and improvements we could implement. That's it. Thank you very much for listening.
Thank you, Martin. Very nice. Okay, we'll go now to the last piece of the puzzle of today's session. I will invite my colleague Jan to show how actually civil engineers can design flood protection measures, and he will also present this on a real life project here in Slovenia. So please, Jan.
Yes, hello. Hi. I will share my presentation. Okay.
Yeah, we can see it, yes.
Okay, just let me do this. Okay. Okay, so welcome from my side as well. I will show you our software for flood protection design, Aquaterra. And let's start with this. So this is a part of Ljubljana. It's a capital city of Slovenia. This is in the year 2014. And as you can see, serious flooding has occurred due to heavy rainfall. On the other hand, in 2023, which was also a year where we had big floods in Slovenia, in that time, this area experienced similar rainfall amount, yet it wasn't flooded. And the reason was that the Slovenian company Zvor designed the plan for flood protection of the Gradaščica River basin, which runs through this part of Ljubljana. This project was funded by European Union Cohesion Fund, and company Zvor prepared the project documentation for the construction of flood control facilities that were implemented in time, meaning before 2023, and this area wasn't flooded because of that. Aquaterra played an important role in this matter since it was used to design the river geometry, and then Mike software was used for the hydraulic analysis. Companies Zvor shared their project documentation with us. So here are a few samples of layout and cross sections. And if you scan this QR code, you can learn more about this success story and also find other customer stories in our website as well. So yeah, Aquaterra is primarily used for river and channel design, flood protection design, torrents and landslide control, and river restoration. However, it can also be used for open channel irrigation systems and also earthworks. So you're able to calculate the quantities like materials in cut and fill and do this section by section. And you can also create the summary table as you can see in the picture. So now I will show you the basic workflow in Aquaterra and how to design flood protection measures with it. Let me just say, if you're just starting with Aquaterra and you need a detailed step-by-step workflow to learn the basics, you can watch our online Aquaterra training course, which is free and available if you just scan this QR code. But today we will go a bit faster through these steps. We will first create the river model in Aquaterra. Then we will export this model to HEC-RAS. You can also do it with Mike, but today we will only show it in HEC-RAS. We will perform hydraulic analysis there. Then we will design a new river channel in Aquaterra according to the hydraulic analysis. We will define a new riverbed, design new terrain in cross sections and add a dike. And then we'll export this designed model to HEC-RAS again and do the hydraulic analysis again and import the results back to Aquaterra. So this is the plan, and let's start with this first step. Let's create the river model in Aquaterra. So here I have some river alignment that I drew with the polyline. And with Aquaterra, you can just use a polyline to alignment tool and you can create a longitudinal alignment. So now this alignment corresponds to the river alignment in the alignment manager because I selected it. Then next step would be to create some sample lines like this, and you can change the starting and ending station, and then you can define the width of the cross axis and the distance between them. And let's just change the scale of these labels to get a better view. Okay, and now we have this alignment and sample lines. and we will create, those are actually placed on elevation 0, and we want to drape them to the surface, but first we need to create it. Here we have some 3D points and 3D polylines, which are a result of geodetic and bathymetric survey. And from this we can create terrain. We will also add some LIDAR points just to get bigger area covered. So like this. And I will just hide those attributes. Okay, so these are the points which we can use now to create the DTM terrain. And you just select all the data that you want to use for creation of DTM, and then you can represent it with triangles or contours. So now we have created this terrain, but I will just hide the triangle so the model will work a bit faster. Now we have created the DTM with Aquaterra, but you can also use BricsCAD or Civil Surface as well with Aquaterra. Okay, so let's go to the top view, and now we can drape the lines, so sample lines and longitudinal line to the surface. What happened now, those zero elevation lines came up to the surface, and now we have them here. So now we can draw the profile view, and we will get the elevation of the riverbed here in profile view, and we can also add cross sections. Like this. So now we have geometry of cross sections, and we also have the alignment, and we can export this using our function export to HECRAS to HECRAS. So if you look now, we go to the second step. We will export the model to HECRAS and do the hydraulic analysis there. Just to show you how you import the Aquaterra geometry, you just go to File, Import Geometry Data, and select HECRAS format. And then this G00 file will get exported from Aquaterra, and you can then check if everything is all right and finish to import data. And now you can see cross sections and the alignment in HECRAS. Then you need to set the model, which I have already done in a different project. So the model looks like this. Let's see it in 3D view. We have added a surface made from LIDAR data, and also we added some buildings into this model. And now if I play this, and we also did some hydrological analysis, we added, of course, the input data for this. And now if I play the animation, here you can see what happens. This river floods the residential area. So what we want to do now is to go back to Aquaterra and design a new channel. So design a new riverbed in profile view, and then also design new terrain in cross sections. And we will also add a dike. I will show you how to do it in a moment. So now here we can add a deeper riverbed with a draw profile view. You can just draw it, or I have saved this profile of this new river bed, and I will just add it here. So this is our new deeper river bed, and we can add it to cross sections with this insert profile option. So now we get this point, which is an elevation of this line actually in cross sections, and we can draw some cross section elements. And in Aquaterra, you can use cross section elements that are typical for river regulation. And for example, you can add channel or dike or embankments. So if I just show you how to do it, you have all the parameters here. You just set them. You can see in the picture which parameter you are setting, and then you can also select on which cross sections you want to add this typical cross section element, and then you click OK, and you will see that this element gets drawn on all the cross sections that I have selected. And I can also add a dike, for example, here, and it also gets drawn on all the cross sections, except from when this is lower than the terrain, because here we want to actually draw embankments. We want to draw them in cut, so I will do like this. And this is how you can add elements on all the cross sections, which makes your process faster. You can also edit these elements if you select it, and then you can here you can change the slope of this embankment, so it changes. And because I have selected only this cross section, it will change only in one, but I can also select more. Then you can also save this typical cross section, this regulation that we just did. You can save it. We save it as a macro, and then you can also play. Actually, you can load this macro, and I have pre-saved a macro here. So I will show you how this is done. I want this to be put on all cross sections. So I select this one, and then this regulation that I already pre-prepared is done on all the cross sections. Okay, and now what we have to do is to assemble a new terrain line, because we want to export this new terrain to HEC-RAS. You just select all the elements that you want to include. So we want to include channel, left and right dikes, left and right embankments, and I will name this new terrain. And now this new terrain is created on all the cross sections, as you can see. So another thing that we want to do, so we have now made this riverbed deeper, and also we have changed the profile of cross sections to be a bit wider, and now we want to also add a dike on this line here. And to do this, I only have to add a new axis, and I will name it dike. And then I will do actually everything I did for the channel, but I already have prepared this so we don't lose time. So what I did is actually I just have made cross sections. I mean sample lines. I draped everything to the surface, and then I made a profile view with this line representing the crest of the dike, and this is this point here. So this will be the crest of the dike, and I will also draw. Wait just a second. Yeah. So I will draw. Let me Okay, so I will draw the dike here. I will use this TCS dike. Again, I prepared this macro in advance, so I can now just run it here. Okay, so now we have a dike here, and actually we have everything we need to go back to HECRAS, but there is just one more step I want to do. So I want to show you how to put this dike in HECRAS so it becomes part of the terrain. So to do this, we will create again the new terrain line. We will select this dike, all the elements, and this will be named and now, because I only want to include this part of the terrain, I will use trim command. This trimming command only works on the cross sections of Aquaterra, but when you use it, it will work on all the cross sections. So you only need to do this on one, like this. Okay, so we only have this part now, and as you can see, it's on all the cross sections. And I want to now export only this terrain, this part of the terrain. I will do it again with HECRAS export to HECRAS. And let's see where we are now. So we have added all these things, and now we will export the designed model to HECRAS. So just to show you first how you create a terrain including the dike. So you would import the dike using import geometry data HECRAS format as we did before for Aquaterra, and you will get the alignment with cross sections of the dike. And then you will go to RAS mapper, where it is possible to use export layer. So to export this geometry, these cross sections and alignment to GeoTIFF. And then when you have, you save it as dike, and then you can add a new terrain. You can create new HECRAS terrain. You select plus button and you just select dike, and you will get something like this. But then if you want to join this to your existing terrain, you just go here, you create a new terrain, you select plus button, you add dike, and you add your existing terrain, which is in our case some leader data. You make sure that dike is above the your basic terrain, and then create. You click create, and you will get something like this. So a terrain which also includes the dike terrain. So this is how you import the dike into HECRAS. And now, now let's see the designed state of HECRAS analysis. So I have it here. And now, if you look what we did, we made this channel wider. We also made it deeper, and we added this dike here. So now let's see what happens with the water, if it also floods the residential area or not. And as you can imagine, I have set everything so we made this regulation in a good way so it doesn't flood the residential area. Okay, so now we go to the last step, which is we will import the results of hydraulic analysis back to Aquaterra. So let's see the Aquaterra. If you go here, okay, we can go to utility and use HECRAS import from HECRAS, and we will then have an option to add water surface levels. You just have to select the right alignment. Okay, so now the water surface level is imported, and you can also add it to the profile view. Surface levels. Okay, so now we also have it here. So this is how you can import the results back. And now let's see another thing. We can also create a planimetry here and quantity takeoff analysis. So I will use a material and then define the polygon which I want to do the planimeter on. This one and this one. So again, you have to select the right alignment. Okay. And now we get the polygon here, and we can make a quantity takeoff. So we insert in the drawing the places of where I want those information to be imported. And now we have here the information of the fill material, quantity, and also I have a quantity takeoff table with all the quantities inside and also the summation of all the quantities. So when you have this planimetry, it is very easy to create a 3D model with Aquaterra. So I will show you in the example of this dike. Or maybe let's go first like this. So you go to utility, and here you can also prepare some properties, your property sets. So this 3D model won't be only a 3D model, but also a BIM model. And you can add your own property sets here. And then when you go to create 3D model, you can select your property set table here. And then when you click OK, this 3D model is then created. Let's show it in shaded view. And now let's also add the terrain like this. So now you can see we have a 3D model of this dike, and we can also, if you go to utility here, you can also edit the properties on this. You can edit the properties on these elements. As you can see, you get automatically the name of the axis, the end and start station, the volume, and GUID the number. But as I said, you can also add your own properties. Then you can filter the elements using these properties, and you can also do the clash analysis or export the model to IFC. So basically you can, this is all the things you can do with Aquaterra. And Aquaterra works on AutoCAD and also on Civil 3D, but also on BricsCAD. We support HECRAS, but also Mike by DHI, which is also software for hydraulic analysis. And And here I have another example where the model was imported to Mic Hydro. So this is on BricsCAD, the same example. This is in Mic Hydro. You have the alignment and cross sections, and then you do the analysis and you get the results. And also you can view the results in Mic Viewer, and you get them like this. So this is all from my side. I will pass it back over to Gregor, but if you have any questions on what we have covered, please feel free to ask.
Thank you, Jan. We can stay on your last slide because this is also my slide. So let me check now if we've reached the final stage of our presentation, is the Q&A, but I was checking the questions. I think we have one for Katya. Do you see the question section, or should I read it for you, Katya?
No, could you please read it? It might also
Okay.
be.
So the question was from one of our guests regarding the water level measurement. If we don't have good sun radiation, will the device provide a good number? I'm thinking if there's no sun on collectors, will it still work?
So this is a very tricky question with not one answer, but I will try to keep it short. So we would always have to check on local conditions. Of course, you can't run a solar powered system without any solar radiation. We have options to just adjust battery size and solar panel size to, based on if we don't have that much solar radiation, maybe we can work with a bigger panel. If that also is not sufficient, we might have to switch back to a battery-only supply where you then have to go change the battery or to check for mains power, which is also an option. And one thing we also do, we are very flexible in the system setup. So with the flood monitoring system, I showed that we can put the solar panel right on top of the system, which is neat and compact and very simple to install like that. But if you don't have a good solar radiation on that spot, because you might be underneath trees or underneath a bridge, somewhere in the shadows, we also have the option that you can put the solar panel completely somewhere else. You just need a longer cable, that's all. And that would enable you to put the solar panel itself in a more sunny location, which would then be more favorable. But yes, of course, you would have to see. We can do basic calculations on how much power we need and how much power we would be able to gain. But solar radiation also has a bit of the disadvantage that you can never really predict what is going to happen. You might have experience in your area how much sun is shining, but you could have a month of rain. You never know. So I would say I live in the Netherlands. Here we had probably one of the most sunny Aprils ever. So this would have been a very good month for a solar powered station. But we also had very rainy Aprils where maybe your solar powered station would have struggled. So yeah.
If I understand correctly, if it doesn't have power, it doesn't do the reading. It doesn't do incorrect reading, correct?
That is correct. The accuracy or the functionality does not depend on how much sun there is. The only point you have, if there's not sufficient solar radiation to recharge your system through the solar panel, then at one point your battery will be empty and the system will completely fail. So without battery or without power, it can't do anything. Also there, we have a few backup things to make sure that the system works as reliable as possible. For example, you could get an alarm if your battery power drops, which would indicate that something is wrong with your solar panel. Maybe it got stolen, maybe it got destroyed, maybe it's covered by snow or dirt. If your battery power drops, you can get an alarm. And then I have to go to the field and check what's wrong before the station stops working. Of course, the batteries themselves. So we do have a buffer battery in there, and that can keep the system running for, based on the choice of battery and solar panel, the battery can keep the system running for a few hours, up to a few weeks, or even a few months. So you could set up the system in a way that you say, I'm fine with a month without sun, and the system will keep running. It will keep operating completely without sun, purely on battery. But yeah, it's really, the system does not get less accurate with less sun. It's just about, do I still have power?
Okay, thank you. Then we have a question, I believe it was already answered. If Aquaterra is an extension in Civil 3D, actually it's a software that can run on top of Civil 3D and or BricsCAD or AutoCAD for that matter. Question, how much is the CGS Labs software, and is there a specific training that can be provided? We can provide specific training depending on your requirements or level of knowledge. Regarding the price, it all depends on the type of the license you want to purchase. So I recommend that you contact us and we can discuss that. And then we have another question. Average or estimate price of mentioned presented project. So this would be maybe for the lakes in Switzerland project and maybe flood protection of Gradaščica River. For the second, we don't have the price that we could share. We could inquire how much was the cost of the project and get back to you. Regarding the Switzerland, Martin, can you maybe share any information?
Sorry, could you repeat the question? It's about the costs of the system, or?
Yeah. Yes, about the cost of the project. I can imagine project implementation or the running costs of the project.
It's hard to guess. So I'm on the project now for almost 2 years. We have a formal agreement and contract with a BAFU. So I'm not sure if I'm allowed to talk about it, but it's like, let's say it's in several hundred K per year, like something like that. And the project is running for, I think now, almost 15 years. So it was started as a very small hydrologic model, and now it's just like it grows and grows and grows. So if you, from zero, set up the model anew in another country, yeah, it will definitely take a lot of money, I think. But also, of course, we have much more experience now and much more things we can copy. I hope that is enough as an answer. I don't want to go into very detailed numbers now. But of course, you can also always reach out and talk to my manager or to me.
Okay, thank you.
And we also have costs for this project, which is 68 million euros. You can read everything on our webpage as well.
Yes, it was European funds. Okay, just let me check. Yeah, these were all the questions. So I think we can wrap it up because we're already 15 minutes over predicted time. I would like to thank you all for contributing to this event. I think that we have covered all the aspects from weather forecast through measurements, through designing projects and maintenance systems. And I hope that this session was insightful and that the attendees get the information that they expected. As mentioned, if you have any questions, let us know, and in the session recap, we'll share the video recording with you with all the contacts from our panelists. So thank you all again, and hope we'll cooperate in the future on some projects as well. Yeah. Bye.
Thank you.
Thank you very much. Bye bye.